Okay, so in the previous video we introduced the mean and standard deviation, and here in this video we're going to look at normally distributed variables which give us a really nice sort of concrete application of the standard deviation and the mean, but the standard deviation is a less familiar thing. So in practice, many variables will produce a roughly symmetric distribution, particularly if a large enough data set is obtained. So if you were to just survey, 10 people and measure their heights, you might not get a very symmetric distribution. But if you were to measure 10,000 people's heights, you would get a roughly symmetric distribution. Okay, even perhaps 100 or 200 people's heights, 1,000 people's heights, you'd probably get a roughly symmetric distribution. So symmetric distributions can be modelled by a bell-shaped curve, which is characteristic of a normal distribution. So when we talk about a normally distributed variable or a normally distributed data set, it is following a roughly bell-shaped curve. Okay? The normal distribution is studied in significantly more detail as part of the Maths Methods course, but we also look at it here in Further Maths in the context that we're going to talk about in this video. So opposite here we have an example of an approximately symmetric distribution represented by a histogram, and we can see from the red line there that it can be modelled by a normal distribution, which is that bell curve, red bell curve. So we already know that when distributions are symmetric, the mean and the median are equal. And a feature of normally distributed variables is they offer us a clear and insightful interpretation of how the standard deviation connects to the spread of the data. So if a distribution is approximately normal, so it approximately follows a bell shape, and it's approximately symmetric, then we know that approximately 68% of the data values lie within one standard deviation of the mean. We'll go through this in more detail in a minute. If we have an approximately normal distribution, that is symmetric and bell-shaped distribution, we know that approximately 95% of the data values will lie within two standard deviations of the mean. And if we have an approximately normal distribution, approximately 99.7%, so pretty much all of the data values should lie within three standard deviations of the mean. These three figures, 68%, 95% and 99.7%, these obviously don't change, and these essentially come to form the 68, 95, 99.7% rule. I say sarcastically the catchy name of, because it's not particularly catchy, it doesn't really roll off the tongue, and it doesn't help you to remember those three numbers, but you essentially need to remember those three numbers. So 68% of the data is within one standard deviation of the mean, 95% of the data is within two standard deviations of the mean, and 99.7% of the data is within three standard deviations of the mean. Okay, let's have a look at an example to see what we mean by that. So IQ is a variable that is known to be normally distributed. In the population, IQ scores are normally distributed, and they have a mean of 100, so the average IQ score in the whole population is 100, and a standard deviation of 15. Okay, so we want to use this information in conjunction with the 68, 95, 99.7% rule to complete the following statements. Approximately 68% of the population have an IQ between what and what? Okay, so we know that 68% of the population will have IQs that are within one standard deviation of the mean. It's a really good idea in these sorts of problems to draw yourself a rough sketch of what's happening here, to draw yourself a rough bell curve. Okay, the mean will be in the middle at the peak. Okay, so that will be the mean in this case, which is in this case that's 100. And then we know that pretty much all of the distribution will lie within three standard deviations. So we're just going to split that into roughly three equal sections. And one standard deviation is 15. So one standard deviation above the mean is 100 plus 15, so it's 115. Two standard deviations above the mean is 100 plus two lots of 15, so it's 130. And three standard deviations above the mean is 100 plus three lots of 15, which is 145. Okay. The other side, 15 less than the mean, is 85. Taking away 15 again, so another standard deviation, takes us down to 70. Taking away 15 again takes us down to 55. Okay, so this is 1 standard deviation above the mean. This is 2 standard deviations below the mean. This is 3 standard deviations above the mean. So going back to the questions, we know that approximately 68% of the population have an IQ within 1 standard deviation of the mean. Now, I haven't drawn myself a perfectly symmetric bell curve here. So within 1 standard deviation of the mean, so mean plus 1 standard deviation to mean minus 1 standard deviation, okay, we're going to get approximately 68% of the distribution. So that means between 85 and 115. So approximately 68% of the population have IQs that are between 85 and 115. The second question is approximately 95% of the population have an IQ between. Now we know 95% is the figure for within 2 standard deviations of the mean. Okay, so 2 standard deviations below the mean is 70, 2 standard deviations above the mean is 130. Approximately 95% of the population is going to lie with an IQ between 70 and 130. Okay. Then part C is approximately 99.7% of the population have an IQ between what and what. So we know that 99.7% is all about being within 3 standard deviations of the mean. So 3 standard deviations below the mean is 55, 3 standard deviations above the mean is 145, and we know that approximately 99.7% of all the data values will lie between IQ scores of 55 and 145. Okay, so our answer to part C, 55 and 145. Okay, then we can use the symmetry. So the whole thing is symmetric. Okay, it's exactly the same either side of there. Okay, my bell curve's not perfect, but we want to use the symmetry. So approximately what percentage of the population have an IQ greater than 100? Okay, so 100 is the mean. It's a symmetric shape, which means that this is 50% of the distribution above 100%. Okay, so 50%, approximately 50% of the population have an IQ that is greater than the mean, greater than 100%. And that's because, so we know exactly 50% of the distribution has an IQ greater than the median IQ, but because we know we have a normally distributed variable, that means a symmetric bell-shaped distribution, mean and median are the same thing in a normal distribution. Okay, part E, approximately what percentage of the population have an IQ between 85 and 100? Okay, so between 85 and 100 is this section in here. What we've got to think about is that we know that between 85 and 115, we know that that's 68% from there to there, and we know that the mean is halfway. So therefore, this must be half of 68, which is 34% in there. Okay. So approximately 34% of the population have an IQ between 85 and 100. Part F, approximately what percentage of the population have an IQ greater than 115? Okay, let's have a look at this. Let me just get rid of those markings from the last one. So greater than 115, so here's 115, it is 1 standard deviation above the mean. We want to think about greater than 115. Okay, so what we want to think about is that we know, again, we want to use our information about the 1 standard deviation. We know that that's 68% in there, okay, from there to there, which means that outside of here has to add to give us 100%. Minus 68% leaves us with 32% for outside, for either side, okay? And then the shape is symmetric. So 32% divided by 2 is 16%, which means we must have 16% up here and 16% down here with 68% in the middle, and therefore everything adds up to 100%. So there must be 16% bigger than 100, with an IQ greater than 115. Approximately what percentage of the population have an IQ less than 70? Okay, so similar kind of logic, but we've got a different value here. Let me just get rid of everything here. So an IQ less than 70. So 70 is 2 standard deviations below the mean. Okay, So we want to know what percentage are less than 70. And it's going to be the same as whatever percentage are bigger than 130. Okay. And remember, we already know 70 and 130 are 2 standard deviations from the mean. We already know that here, within 2 standard deviations of the mean, between 2 standard deviations of the mean, that's 95% in there, which leaves a total of 5% for either side, which means we must have 2.5% up here and 2.5% down here because it's a symmetric distribution. So the percentage of people with IQ scores below 70, 2.5%. Okay, so the bottom 2.5% have IQ scores below 70. Okay, and then the last three, approximately 2.5% of the population have an IQ higher than. Now, I actually shouldn't have erased all that because that we can just use the symmetry. We learnt from the previous question that there's 2.5% below here, okay, and 70 is 2 standard deviations below the mean, okay, so it's 2 standard deviations below the mean. So therefore, the symmetry tells us that if we go 2 standard deviations above the mean to 130, this will also be 2.5% above here. So 2.5% of the population have an IQ higher than 130. And then the last two, approximately what percentage of the population have an IQ between 85 and 130? Okay, again, let's work out what we're dealing with here. Alright, so 85 is here and 130 is here. So 130 is 2 standard deviations above the mean. 85 is 1 standard deviation below the mean. Okay, so again, let's think about the mean. Alright, so we know between 85 and 115, 1 standard deviation within the mean, that's within from the mean, is 68%, which means that if I've only got half of it, this must be 34% in here, half of 68. We also know that within 2 standard deviations of the mean, so from 70 to 130, we know that's 95%, which means if I'm only interested in this bit over here, half of that, half of 95% is 47.5%. If you need help with that, just get your calcs. 95 divided by 2 is 47.5. And so therefore, between 85 and 130, between 85 and 130, that's 34 plus 47.5. Sorry, that's wrong. 1, 2, 3, 47.5 plus 34. So we have 81.5% in between here. So 81.5% between 85, IQ scores of 85 and 130. The other way you can do that is rather than think about halving 68% and halving 95%, we can do what we did for some of the examples above, and we can think about, okay, we know within 2 standard deviations of the mean, it's 95%, leaves 5% either side, which means there's 2.5% up here, above 130. Same logic, we know within 2 standard deviations of the mean, that's 68% in there, so we have 100 minus 68, 32% that's not in between there, and because of the symmetry it means it'll be 16% either side, so this will be 16% down here. So if we do 16 plus 2.5, plus 2.5, that's 18.5% that are outside of the area that we want, so the area that we want will be 100 minus 18.5%, which is indeed 81.5%, which is what we worked out here. Alright, last question. What percentage of people have IQ scores that are, let me go back. Approximately what percentage of the population have an IQ less than 55? Sorry, I've just erased that. That's 55 over there. Okay, so here's 55 down here. That is 3 standard deviations below the mean. Okay. We know that within 3 standard deviations of the mean, all of that, we know that that is 99.7%, which means outside of that, added together, has to be 99.7% minus 100 is 0.3% left to go either side. because of the symmetry, it'll be the same percentage at both sides. So half of 0.3% is 0.15% for here, and 0.15% for here. Again, you can do this maths with your guys. 100 minus 99.7 leaves you with 0.3% outside, and divide that by 2 leaves you with 0.15% on either side. Okay, so 0.15% of the population will have an IQ less than 55. Alright, example 2. The distribution of the heights of students at a primary school is approximately normal with a mean of 132 centimetres and a standard deviation of 11 centimetres. What percentage of the students have heights greater than 132, between 132 and 154, less than 110? Again, the first thing I would be doing is constructing myself a bell-shaped curve with the mean at, what was the mean, 132? And then we want to think about our 3 standard deviations. 3 standard deviations above the mean, 3 standard deviations below the mean. So the mean plus 1 standard deviation, so 132 plus 11 is 143, plus 11 again is 154, plus 11 again is 165. 132 take away 11 is 121, take away 11 again is 110, take away 11 again is 99. So important to work out what are those values that are 1, 2 and 3 standard deviations above and below the mean, because that's going to help you answer the questions. So part 1, what percentage of students have heights greater than 132? Well, 132 is the mean, so there'll be 50% above there. Okay. So 50% of students will have heights greater than 132 centimetres. Part 2, what percentage of the students have heights between 132 and 154? Okay, 132 and 154. 132 is the mean. 154 is 2 standard deviations above the mean. Okay, so we know within 2 standard deviations of the mean is 95%. Okay, so therefore between there and there will be half of 95%, which was 47.5%. Alright, and then part 3, less than 110. Okay, we can stick with the diagram we've got here. So we know we had 95% here. Let's get rid of that. We don't need that one. We've got 95% in there, between there and there, which means there's 5% left in total. Okay, which means this must be 2.5% above 154 and 2.5% below 110. So what percentage of students have heights less than 110 centimetres? 2.5%. Part B, if there are 600 students at this primary school, how many have heights between 121 and 143? Okay, so 121 and 143. Let's just get rid of that. Okay, so 121 and 143. So that is 1 standard deviation either side of the mean. So we know that that's 68% between those two values. So we know it will be 68% of the students, which is equal to 0.68. 68% is 0.68%, divide by 100, which means we get 0.68, of times the number of students, which is 600. So 68% of 600, 0.68 times 600 is 408 students. So 408 students will have heights between 121 centimetres and 143 centimetres, and that's equivalent to 68% of the students. Okay, complete the following generalised normal distribution diagrams so that you have a reference point for solving problems. So if we think through this diagram, this general diagram, you then should be able to answer any of these problems really efficiently yourself. Okay, so we already know I've filled in our 68, 95 and 99.7. So we already know that between here and here, that is the mean minus 1 standard deviation and the mean plus 1 standard deviation, we get 68% of the distribution. Okay, between here and here, we get 95% of the distribution. So that is between the mean minus 2 times the standard deviation and the mean plus 2 times the standard deviation. There is 68% of the data. And then finally, between here and here, that is the mean minus 3 standard deviations plus the mean, to the mean plus 3 standard deviations, we have 99.7%. Okay, so then we can use all our symmetry. So obviously if we've got 68% from here to here, it'll be half of that here, 34% in there, and 34% in there. Okay, similarly with the 95%, we know that it's 95% all the way from there to there, which means that it is half of 95%, 47.5% from there to there, okay? Which means if we only want to know from there to there, okay, we know that bit's 34%. We know together they have to add up to 47.5%. So we do 47.5 take away 34 to work out what's going to be left here, 13.5%. Okay, so this bit here will be 13.5%, 13.5%, and then we can use similar logic again. So we know that we have 99.7% the whole way from there to there. Oops, sorry. We know that, therefore, that means that here to here will be half of 99.7. 99.7 divided by 2 is 49.85%. Okay. And then we already know, if we add up those and those, that we've got 47.5% from there to there. And so that means the bit out here, sorry, not from there, the bit from here to here will have to be 49.85 take away 47.5. 49.85 take away 47.5. Okay, so there's 2.35 out here. Okay, so 2.35% in there, and that's not out there forever, that is to there, okay, from there to there. And so we've also got 2.35% there. And then we've already worked out these last bits out either side. We've done this previously. We know that from here to here that's 99.7%, which means there is 0.3% left to be shared with either side. Dividing that by 2 for the symmetry means we have, sorry, divided by 5, not by 2. Dividing that by 2 means that we have 0.15 out here and 0.15 out here. Okay. Alright, 0.15. And then we can work out these ones just by adding together some combinations. So if we take the 0.15 for there plus the 2.35, sorry, that looks a bit like an 8, I'm just going to fix that. 2.35. If we add those together, that will give us that. Okay, so 0.15 plus 2.35, so that's 2.5. We already know that. That's the bit either side of the 95 bracket. So we know there's 95 from there to there, and therefore 2.5 out there and 2.5 out the other side. Okay. Again, we can use those facts, or we can simply take the 2.5 that we just worked out is here and add on the 13.5 to get that total distance there. So 2.5 plus 13.5 gives us 16%. Again, we can use that, also think about that from the 68%, sorry. So again, if there's 68% in here, then subtracting 68 from 100 is 32%, which leaves half of 32%, 16% for either side. Okay, so we've got 16% there, and then obviously from the mean and above, that is 50% in a normal distribution. Okay, so then you should really be able to take any question you get, whether it's, about IQ scores or whatever, where that's 100, and simply work out, well, if it's IQ scores, that's 100, that's 115, that's 130, that's 145, that's 85, that's 70, and that's 55, and therefore I can answer any questions I want. So if I want the proportion that are between 115 and 130, that's 13.5. If I want the proportion with an IQ score less than 85, okay, that's the same as bigger than 105, which is 16%. If I want the proportion that are between, 70 and 115, I can add up 34 and 34 and 13.5. Okay, so all the numbers I need are here and summarized for you to be able to now solve problems. Okay, the next thing we want to talk about here is standard scores. So now that we have an understanding of the 68, 95, 99.7% rule, we find that the standard deviation gives us a meaningful interpretation of the spread of the data. So it tells us, right, okay, 68% of the data is between here and here, 99.7% of the data is between here and here, etc. So let's suppose that two maths classes sit two different tests on the same topic. Both tests were marked out of 100, and the results in Class A are normally distributed with a mean of 62 marks and a standard deviation of 12 marks, whereas the results in Class B are normally distributed with a mean of 69 marks and a standard deviation of 10 marks. Adrian is in Class A, and he scored 74 marks on his test. Ben is in Class B, and he also scored 74 marks on his test. Can we directly compare Adrian and Ben's scores and conclude that they performed equally well on this topic? So the key is to understand that the overall performance on the two tests was different, okay? So the first test, Class A, was a mean of 62 and a standard deviation of 12, and the other test, Class B's test, was a mean of 69 and a standard deviation of 10, okay? So Class A have a lower mean but a higher standard deviation. So a lower overall mean, but the data is more spread out. Class B have a higher mean but a lower standard deviation. Okay, so a higher measure of centre but lower spread. So it's difficult to compare their raw marks. Okay, and so this is where we want to be able to standardise their scores so that we can directly compare them. So what we actually want to do is consider, well, how many standard deviations above or below the mean is a score of 74 in Class A and in Class B? How many standard deviations away from the mean is that? So in Adrian's class, the mean mark was 62, which was Class A. The mean mark was 62 and the standard deviation was 12. Adrian's score of 74 marks is 12 marks above the class mean. So his performance was exactly one standard deviation above the mean in his class. And so that means that he scored more highly than 84% of his peers. So we know that because if it's one standard deviation above the mean, one standard deviation above the mean is here. And if we add up all of these, we get 84% here. And we can see above here we've got, 16% here. So that places him at the 84th percentile, essentially. Okay. Whereas, and so we say that Adrian's standardized score, and we call that a Z score, is a standardized score. His Z score is +1, indicating that it is exactly one standard deviation above the mean, hence the plus. In Ben's class, the mean mark was 69, and the standard deviation was 10. Ben's score of 74 is 5 marks above the class mean. So that's half of a standard deviation above the mean. So we would say that Ben's standardized score, or his Z score, is +0.5. He sits 0.5. He sits 0.5, half a standard deviation above the mean in his class. Okay, so we don't have an exact percentage for that. Whereas here we could say that meant he's in the top 16% in the 68, 95, 99.7% rule. We can't refer to half a standard deviation above the mean. So we can't get a percentage value, but we know that it's clearly going to be, he's going to not be as high, he's not as high up, relatively speaking, in his class as Adrian is. So whilst both boys performed better than the majority in their respective classes, we can conclude that Adrian's performance was better than Ben's when their scores are compared to the performance in their respective classes. So standardized scores, or Z scores, measure how far above or below the distribution mean a data value sits. For example, a Z score of -1.5 suggests that the score is 1.5 standard deviations below the mean of the distribution. To calculate a standardized or z-score from the data value, we use the following formula. The standard score, or the z-score, is their actual score, take away the mean, divide by the standard deviation. So if we go back up to check what happened, what we did here in this paragraph here. So Adrian's z-score is going to be his actual score, which is 74. Take away the mean in his class, which was 62, and divide it by the standard deviation, which was 12. 74 minus 62 is 12, and so we get a z-score of 1. It's a positive 1. Okay. In Ben's class, okay, his z-score is going to be his actual score, which was also 74. Take away the mean in that class, which is 69, and divide it by the standard deviation, which was 10. 74 divided by 69, minus 69 is 5. 5 divided by 10 is 1/2, or 0.5. Okay. Alright, so that's our formula. So what would it mean if someone had a standardized score, or a z-score, of 0? Remembering that standardized score tells us how far away from the mean their score is. Okay, so if you've got a z-score or a standardized score of 0, your data value isn't at all far away from the mean. It is, so therefore it must be the mean. Okay, what does it mean if the standardized score is 0? That the actual score equals the mean score. What does it mean if the standardized score is positive? So if you have a positive standardized score, that tells you that your score is above the mean. Okay, that the actual score is, above the mean. Whereas if we have a negative standardized score, we are told that means that the actual score is below the mean. Okay, example 3. In her VCE exams, Sarah achieved 82% in her Further Maths exam and 76% in her Maths Methods exam. The marks in both exams were normally distributed. In Further Maths, the mean mark was 57% and the standard deviation was 21%. In Maths Methods, the mean mark was 50% and the standard deviation was 23%. Calculate Sarah's standardized z-scores in both exams. Okay, so in Further, her z-score is going to be her actual Further score, which was 82%, minus the mean in Further, which was 57%, and divided by the standard deviation in Further. Standard deviation in Further was 21%. Okay, so 82 minus 57 divided by 21. Control Enter. We should say, let's go with z-score to 2 decimal places. The question should tell you that. My apologies. So it's going to be 1.19, her Further Maths z-score, whereas her Methods z-score she got 76% minus the mean in Methods, which was 50%, divided by the standard deviation, which was 23%. So it's clear that in Methods there's a lower mean and a higher standard deviation. In Further, higher mean but lower standard deviation. Okay, let's work out the Method z-score. So Control divide for the fraction, 76 minus 50, 76 minus 50 divided by 23 is approximately 1.13. So which subject is the better result for Sarah? Well, actually they're pretty similar results. They've got pretty similar z-scores, even though, her Further score is higher than her Methods score, but actually at the end of the day, when compared with the performance in those cohorts, they're similar scores. And actually that, in a nutshell, it's not, the maths is not as simple as this, but that's essentially what the scaling is trying to do. Okay, work out kind of relative to the cohort, where do you sit, so that we can then compare those scores across subjects. Alright, so which subject is the better result? Further Maths is the slightly, it's really only very slight in this case, slightly better result. So relative to the other students in further maths, she performed slightly better than she did in maths methods compared to the other maths methods students. Okay, so the work today for normal distribution and Z standardized scores is from 2G and exercises 2G and 2H.